Welcome back to Data Explained channel, where we make complex topics easy to understand. Today, we talk about data boundaries, precision limits. All data representations have limits. One of the most important and most misunderstood of these limits is precision. Precision limits describe how accurately a data representation can capture and preserve information. They define the boundary between what can be represented exactly and what must be approximated. These limits are not implementation flaws. They are inherent consequences of representing real-world information using finite systems. In the physical world, many quantities are continuous. Time, distance, temperature, and probability do not naturally come in discrete steps. But digital systems are finite. They store data using a fixed number of bits. As a result, continuous values must be approximated. This is where precision limits arise. Consider numeric representation. When a number is stored using a fixed number of bits, only a finite set of values can be represented. Any value that falls between those representable points must be rounded. Floating point numbers are a common example. They allow a wide range of values, but not all real numbers can be represented exactly. Even simple decimal values such as 0.1 cannot be stored precisely in binary floating point form. The result is rounding error. Individually, these errors may seem insignificant, but as computations accumulate, rounding errors can compound, leading to measurable deviations from expected results. This is why precision matters in scientific computing, finance, and engineering. Precision limits are not restricted to numeric data. Time is often represented using timestamps with fixed resolution, such as milliseconds or nanoseconds. Events that occur between those intervals are indistinguishable within the data. The representation defines what can be observed and what cannot. Measurements introduce similar constraints. Sensors report values with limited resolution. The data may appear precise, but it is bounded by the granularity of the measurement system and the representation used to store it. Precision is often confused with accuracy, but they are not the same. Precision describes how finely a value is represented. Accuracy describes how close that value is to reality. A system can be precise but inaccurate, or accurate but imprecise. Representation limits directly affect precision and indirectly constrain achievable accuracy. Another important aspect of precision limits is range. With a fixed number of bits, increasing precision usually reduces range, and increasing range usually reduces precision. This trade-off is fundamental. It appears in integer sizes, floating point formats, and fixed point encodings. Designing a data representation always involves choosing where to place these boundaries. In data analysis and modeling, ignoring precision limits can lead to subtle errors. Comparisons may fail unexpectedly. Equality checks may behave inconsistently. Small differences may be lost entirely. In distributed systems, precision mismatches between components can cause data divergence. In long-running systems, small numeric errors can accumulate into large inconsistencies. Precision limits also shape what questions data can answer. If data is aggregated too early, detail is lost permanently. If values are rounded or truncated, the original information cannot be recovered. Representation choices determine not just how data is stored, but what insights remain possible. Understanding precision limits means understanding the boundaries of representation. It means recognizing that data is not reality. It is an approximation of reality, constrained by encoding, storage, and computation. Professional data work, requires acknowledging these limits, designing around them, and communicating them clearly. Because when representation limits are ignored, errors do not disappear. They become invisible. And invisible errors are the most dangerous kind.